coding Microsoft Teams นี่ก็ใช้เวลานานเหลือเกินในการ record. Okay. All right, so let's resume our lecture after a little bit of detour on the discussion, including like how do not call list works and how some problem in IT and computer, like basically problems in technology can be solved with like regulation rather than technical defense, because sometimes technical defense is really hard to guard against every single attack, right? Let's switch here and come back to our lecture. The content, now we are switching gear again to a new concept called superscalar. We talked about this a little bit, right? So we need to go back to lecture 3 when we talk about multi-cycle execution. And what we observe, or at least I assume in the lecture, right? I told you that this is the truth, right? Each instruction takes a different amount of time to run. The add instruction might take longer. The multiply instruction will be shorter, right? I think that's wrong. Sorry, this lack of sleep. Add is faster. My bad. Add is going to be faster than the multiply. Multiply basically is a bunch of add and shifting, right? So we can actually try to schedule instruction using a different number of cycles across all the execution units. But the problem is when you finish the write back stage, when you finish the instruction, the programmer has to see that the instruction finished line by line by line. The fact that the programmer had to see that it finished line by line by line, we call this sequential ordering. Sequential ordering means that whatever I see in assembly, when I compile and it spit out some assembly code that you can see, that the programmer can see, the effects on how it executes has to finish in that exact order, right? If I have an add and then a multiply, and internally you do multiply first and then doing the add, what you need to make sure is when you finish the write back, it goes back to the same order because the ISA required sequential semantics, right? So let's revisit the idea behind superscalar architecture. So this is a recap to make sure you are now back in the lecture 3 and 4 material, all right? So let's assume we have an in order instruction retire. Basically, this means that write back stage follow, right? Program order. When I say program order, this means that if I see assembly code goes this way, it follows that exact order. This code goes first, followed by the next line, followed by the next line, followed by the next line. And we need to maintain that. If I am stalling, something block my pipeline, superscalar architecture say that, hey, I mean, why can't we fetch more? I mean, we can keep fetching as long as we have a buffer for that, right? So as long as we have some additional buffer, as long as I have some storage to store the fetch instruction, right? I can keep fetching. And then if I have an add and a multiply instruction, I can just distribute them, right, to the adder and to the multiplier, right? As long as we modify the register file in the same order as my assembly code, we're good, because the programmer will never notice that this happened internally, right? So this means that I can execute the instruction out of order. For example, this is your code, right? So the code looks like this. Add 1, add number 1, multiply number 1, and then I guess add number 2, right? So that's my code. add number 1, multiply number 1, and then add number 2. What I can do is this. So now let me break this into a 5-stage pipeline for you. Right? So you have fetch, you have decode, you have execute, right? And in execute, you have the adder, and you have the multiplier. And then you have the memory, and you have the write back, right? So what you can do is inside the decode, you have this instruction window. Let's imagine this is a table, right? That contain the fetch instruction. So the add number 1 comes in. Move to this slot, add 1, right? And then the multiply come in. Number 1, right? Move here. Number 1. And then the add number 2 come in here. Move to the 3rd slot here. Right? And then this table will keep go on and on and on. And then there'll be a scheduler in the decoder that say, hey, OK, I have the adder free, so I'm going to dispatch the add number 1 here. And then multiplier is also free, so I'm going to dispatch multiply here. Right? They would perform the add and multiply in parallel because I have the resource to do so. And then let's say the add finish first. I can even dispatch add number 2 afterward while multiply are doing that multiplication, right? As long as in the write back stage, you finish in this order, add number 1, then multiply, and then add number 2. So again, this is a requirement, right? This is a requirement. So any questions so far? มีคำถามไหมครับ ก็คือ point ของเราก็คือว่าเราจะต้องสามารถคือถ้าสมมุติเรามี adder หลายๆตัว multiplier หลายๆตัวเนี่ยเราก็ fetch ทุกคำสั่งมาก่อนได้เลยใส่เข้าไปใน Windows ตัวเนี้ยแล้วสมมุติถ้า adder เราฟรีเราก็ยิงไปเลยยิงไปแบบใน order ไหนก็ได้ตราบใดที่เรามี input ของ add ครบ input ของ multiply ครบอะตราบใดที่ไอ้ write back stage สุดท้ายอะมันอัปเดตด้วย order เดียวกับ order ของโปรแกรมเราอะทุกอย่างจะเซฟนะครับทุกอย่างจะเซฟมีคำถามไหมครับ So basically that's super scalar, right? Now let's do a quick recap on the requirement, right? Basically, you first fetch the instruction to decode stage, right? We can add the instruction window. Basically, these are buffers that store instruction waiting to be run. It stores all the instruction that you are waiting to run, right? Then when you're in the decode stage, you dispatch, right? You dispatch the instruction that are ready. I have all the inputs. The execute unit is ready. I can fire them off, right? And then the processor would contain multiple types of the ALU. I have adder, I have multiplier, I have the logical units that do AND or XOR, right? I can fire off multiple instructions together. And then it would issue instruction when the designated ALU is available, right? This is basically imitating data flow program. It imitates data flow execution, right? The big requirement is you have to retire instruction in the same order as it comes in. You have to retire instruction in the same order as it comes in, right? So that's super scalar architecture. Now, what are the key issues? One of the key issues is called precise exception. So what are the exceptions? Can someone tell me some example of an exception? Have you run a program, even Python or Java program, and you run into exception? Anyone here? Have you tried to divide by 0 in a program before? Anyone? Sure, you have to have done this at some point in time. Divide by 0. So a quick recap on exception, right? Exception is internal to the running thread and is basically as you run your program, if you detect exception, the process would handle that. For example, when you have to try and catch, that can be used to test exception, right? And the priority is ranked based on the process priority. Interrupts are external to the running thread. For example, I hit the power button. I set the interrupt to the running program, say, hey, I want to shut down the computer. This is handled when convenient, and it is actually done by DOS, and priority again is varied, right? Precise exception means that whenever there's an interrupt or exception happening to the computer, right? When exception or interrupt occurs, all the previous instructions should be retired. And then no future instruction has to, anything in the future has to make sure it stays in the pipeline. It's never get written back, right? So again, let's say you have fetch, decode, execute, memory, and write back, right? You run the code this way. And then instruction 1 is here, instruction 2 is here, right? Instruction 3 is here, instruction 4 is here, instruction 5 is here. And let's say exception happened right here, right? Here's an exception. When exception happen, for example, divide by 0 exception, right? You accidentally divide something by 0. The computer would stop. And it would stop in the state that instruction 1 finish, instruction 2 finish. These 3 things is stalled in the pipeline, not executing, right? That's how you handle exception. And that's precise exception. It's basically have to be done precisely at that particular instruction where exception happened. Why is this? Because we have one Neumann ISA, assume precise exception. This helps software debugging. Otherwise, you can't tell when that exception would happen. You have weird ordering of your instruction. Allow for easy recovery, because let's say you handle the exception, you can then resume anything afterward. And also make it easy to restart the process, right? It's easy to restart the process. The issue here is, let's say you have out of order instruction dispatch, right? So let's say your ordering of the instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, and you have your superscalar architecture here. Right, your fetch, decode, execute, memory, write back. Over here, you're finishing up instruction 1. You do out of order internally because instruction 1 and 2 are long. So instruction 3 sneaks in here, followed by instruction 2, instruction 4, and instruction 5, right? Going back to the earlier scenario, exception happened right before instruction 3, 4, and 5. So over here, you want to make sure this finish, you stall the other 3. How do you do that, right? So quick recap right now. Any questions? Any question about this particular problem? มีคำถามไหมครับ ก็คือถึงแม้ว่าเราจะใช้ in order คือโปรแกรมเราอ่ะมันจะทำงาน in order ก็คือรันบรรทัดอ่ะใน CPU ของเราถ้ามันเป็น super scalar ครับมันจะมีบางกรณีที่จะมี instruction ที่แบบแซงเพื่อนขึ้นมาเพราะว่าเราเร็วกว่าแล้วมันก็จะไปรอกันอยู่ตรง write back ก็คือมัน write back ทีหลังได้ตาม order นั้นแต่ถ้าเรามี exception ปั๊บตุ้มขึ้นมาเนี่ยเราต้อง make sure ว่าเวลาเรา pause และ exception ที่เกิดขึ้นน่ะต้องกลับมาเป็นโปรแกรม order เหมือนเดิมก็คือสมมุติ exception เกิดขึ้นที่ instruction ระหว่าง instruction ที่ 2 กับ 3 แบบ instruction ที่ 3 divide by 0 เฉยเลยอะไรเงี้ยเราต้อง make sure ว่า instruction ที่ 1 กับ 2 มัน write back ให้เสร็จ แล้ว instruction ที่ 3 ก็จะเป็นคน raise exception divide by 0 เสร็จแล้ว instruction ที่ 4 กับ 5 ที่อยู่ใน pipeline น่ะต้องหยุดนะครับมีคำถามไหมครับอันนี้เคลียร์หรือเปล่าเคลียร์นะโอเคเพราะพาร์ทนี้คือสมัยก่อนตอนเราสอนพาร์ทที่เด็กๆงงก็คือสรุปก็คือเวลามี exception นะฮะเราต้องปรับมาเป็นโปรแกรม order ซึ่งก็คือบรรทัดที่ 1 2 3 4 5 6 7 ต้องรันตามนั้น แต่ว่าใน pipeline ของเราอ่ะมันอาจจะไม่ได้รันด้วย order นั้นอยู่เพราะฉะนั้นเราต้องสร้างดีไซน์ของฮาร์ดแวร์ให้มันกลับมารันตามนั้นให้ได้ตอนเรามี exception นะครับขอศัพท์ภาษานะศัพท์ภาษาอังกฤษ Alright, so the issue here is how can we ensure precise exception, right? So the naive idea, right? We always start with the naive idea, and it's basically the baseline is not great, right? But it's a good starting point. One thing we can do, every instruction takes the same amount of time. So if I have instruction going into the pipeline first, they will finish first. Simple, right? If I go into the pipeline first, I finish first. And every single instruction take the same amount of time. Is that a good idea or a bad idea? And as we learned, that's a horrible idea, right? This will solve the problem because if I shoot out and fetch, basically if I fetch the instruction first, it would take the same amount of time. Internally in the pipeline, nothing ever get reordered. So that solves the problem. But the downside is really, really bad because your performance tanks, right? Your instruction is as slow. It's going to be as slow as the slowest instruction, right? So we need other method to maintain this sequential state, right? There are multiple structures that we can use, and we can use a combination of these things, but we'll first focus on the first structure called the reorder buffer. The reorder buffer, the point of the reorder buffer is to make sure that we can reorder the instruction back so that it finishes in order, right? So that's a technique to maintain sequential state. We will now go into a little bit more detail on how to implement the reorder buffer. But let's go with the first thing that we have to cover. What's the key idea of the reorder buffer? So internally in the pipeline, right, I can do any order. I can do instruction 1 followed by 4, followed by 7, followed by instruction 2 and 3, followed by instruction 10 in any order. I just need to make sure in the write back stage, right? When I want to update, the register, I do that in order. So update my register file, right, in order. That sounds simple. And I mean, conceptually, it's really simple. I just need to make sure I have this buffer at the write back stage to queue up all the instruction to make sure I have this in order queue, instruction 1, 2, 3, 4, 5, 6, 7. That's it. That's the reorder buffer. Right? So how do we do that? During decode still is in order. Execute, memory, and write back can be out of order because, again, add takes fewer cycle than multiply, right? And many more. Like memory instruction will take longer. So we can do things out of order internally. During decode, that's when everything's still in order. You fetch into instruction window, right? So you have instruction window in here. And then you fetch, basically you fetch things in here. Then you fetch thing line by line by line by line by line. That's in order. So when you fetch new item in here, right? You then allocate this reorder buffer, right? In the same order as you fetch. So it's going to be the same order in a reorder buffer. And I'll maintain the status of that instruction And I only kick out the oldest instruction in the reorder buffer. So when the oldest instruction in the reorder buffer is done, I kick them out, I update the register file, and then I maintain the rest. And I'll keep doing this every single cycle because that would give me the same order. All right, I'll basically get right back to happen at the same order as the instruction coming in. So the question is, how do we build this? Right? Conceptually, it's simple. You want to make sure write back happen at the same order as what you fetch. So how do we implement this reorder buffer? What has to be stored in them, right? First of all, valid bit, 1 bit only. If it's 1, it means that this entry is used. If it's 0, this entry is not valid. No one is using it right now because everything is in hardware. You have to tell the hardware, is this used or not used? So that's the first thing. You need a valid bit. The second thing you need is the destination register and the destination register value and ID. This is basically so that you can update, right? So you can hold the data in the ROB and update the register file when need to. This is basically for the case where you have things out of order, but you already finished that add and multiply. It's just someone else that are a lot slower is waiting for their data. So you just need to make sure that, okay, this instruction has to write this value to this register, and you can hold that until it's your order to update the register file. Again, for the store address and store value, so this is basically load and store instruction. When you have to deal with the memory, right? You have to figure out what's the order. Then the instruction type, does it go to the memory and update the memory, or does it go to the register file and update the register file, right? You can break the two instruction type, the load and store and compute as well. But generally, right, when you have the reorder buffer, right, when you have the reorder buffer, your input to your ALU, basically now register value, right, can be at before the reorder buffer is either in the register file or the forward path, right? When you have data forwarding. But now you can also have future version of your value in the reorder buffer. So this is the new thing coming in. Again, you might be a little bit confused right now. We'll go through some example to make it clear. All right. Now we have 3 versions of the data. The question is, which version should I use for my input? Let's say I have future instruction coming in. I use R1 plus R2. I want to write the result into R3. Where is R1 and where's R2? Which version of it should I use? So that's the first question. To actually access my value, right? One solution, because you have multiple versions of your data, right? So solution we can use indirection. The first thing we can do is to check the register file. And if the register file has the valid bit of 1, it means that I can use this value. If the valid bit is 0, it means that that value is not valid because someone is having the new and updated version of this. If not valid, then check the reorder buffer. Then you can access the reorder buffer later, right? And basically, this would give you the mapping between the register ID to the entry in the reorder buffer, right? So let's say, for example, right, you have 2 instructions coming in. I have add R3, R1, R2, and then add R3, R3, and R2. The first instruction, have R1 plus R2, write the result into R3. The second instruction, want to use R3, also want to use R2 and write the result into R3 again, right? And let's assume that initially R0 has the value 1, 2, 3, 4. Sorry, let's just do for the simplicity, right? R0 has the value 0. R1 has the value 1. So this is the value. And this is the register ID. All right. Now, this is my reorder buffer, right? My bad. This is my instruction window. This is my reorder buffer, right? So when I fetch the first instruction, I need R1 and R2, right? What does the first instruction write the result into? What does the first instruction write the result into? What register is that? R3, right? R3. So here's what I do. First of all, I said I need R1 and R2, right? In the register file, I need to add the valid bit. And initially, everything is valid. Initially, everything is valid. So it's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I have the first instruction coming in. I want R1 and R2. I check the register file. R1 is valid. R2 is valid. What's R1? 1. What's R2? 2. So what's the result of R1 plus R2? R2, my bad. That's 3, right? That's 3. So here is what happened in the reorder buffer. Again, this is valid bit. This is the register ID. And this is the value, right? So the first entry I will add is valid. Register ID is 3 because I want to write the result into R3. The value is unknown until I finish the add. The value is unknown until I finish the add. Then when I kick off this instruction, what would happen here is now R3 becomes invalid in the register file. Becomes invalid in the register file. What happened when I have to process the second instruction? When I'm here, what happened? I'll give you about a minute to think about it, right? How do I correctly process this? So what are the two sources? What are the two registers that we are adding for the second instruction? We add R2 with what? With R3, yes. So is R3 valid in the register file? Because again, the first thing I'll check is that valid in the register file? R2 is valid. The value is 2. R3 is that valid? It's not valid, right? So what do I do next? I cannot use the version in the register file. So what do I do? What do I do? Where do I search? Where do I search? Who might have the updated version of R3? The reorder buffer, right? Because the register file doesn't have that. I will check the reorder buffer. And now I check the reorder buffer. It's not available yet. So I can check the forward path inside the pipeline.
แต่ว่าเรายังไม่มี value ตรงนั้นไม่ใช่เหรอคะแต่คือ
ใช่ ก็คือการที่ไม่มี value อะครับตรงเนี้ย มันจะเป็นการบอกว่าเฮ้ยมันอยู่ใน pipeline แหละเพราะว่า register file ไม่มี reorder buffer ก็ไม่มีเพราะฉะนั้นตอนนี้มันอยู่ใน pipeline แน่ๆคือถ้าเราทำ data forwarding เราก็อาจจะสามารถดึงมาได้แต่ถ้ามันมี value สมมุติว่าผมทำ add ตัวนี้เสร็จแล้วพอดีเลยทำ add ตัวนี้เสร็จมันก็จะเป็นค่าของมันก็คือ3อัปเดตใช่ไหมแล้วถ้าสมมุติใน reorder buffer มี instruction ก่อนหน้าที่เป็นของเพื่อนที่ยังไม่เสร็จมันก็เราจะรู้เลยว่าโอเคถ้าเราต้องใช้ R3 เอาค่า3ไปใช้ได้เลยครับ so basically we first search the register file then we search the ROB and then the third step search forward path in the pipeline. So my second thing I want to point out here is that when I say search the ROB, we can be a little bit smart about how we search because we can mark each row here by an entry ID. For example, row A, row B, row C, row D, row E, right? Then instead of having invalid and number 3 in here, I can change this. And I can say, hey, if you want that R3, go look at row A. Row A would point here. So you don't have to search the entire ROB. It would point to the row that contain the newest version of R3. And then depending on the value here, it can be an updated value or invalid. If it's not valid, then you search the data forwarding path. All right. So that's it, right? But again, with the reorder buffer, now you can finish things in order because this is the order that are in the program order from top to bottom. You just kick out the topmost one at a time, and then you go down and down and down and down, right? Now, what's the problem with reorder buffer? Let's say you have this code right here. How many different versions of R3 are we dealing with? So let's assume this is the source. My bad. Let's assume this is the destination and this is the source. You have this version of R3, this version of R3, this version of R3, right? So you basically have initial version of R3. And then let's assume this is instruction A, instruction B, instruction C, D, and E. You have then the initial version of R3. You have the R3 for instruction A. You have R3 from instruction C. And you have R3 from instruction E, right? Again, not only that, you also use a different version of R3 right here, right? You also use a different version of R3 right here. For this guy, which version of R3 am I using? So this is version 0, version 1, version 2, and version 3. Which version of R3 do I need for instruction B? From A, right? Version 1. You need this R3. This guy needs this R3, version 2 that come after instruction C. Now you need 2 different versions of R3, right? Each of these R3, now ideally, what you want to be able to do is be able to store each version for each of these instructions, right? This technique, we can solve this problem. So this is one of the problems with the initial version reorder buffer. You can't store 10 different versions of R3. So we'll use a technique called register renaming, right? each R3 have its own version, has its own version. How do we do that? So here's register renaming. If you run this out of order, for example, if you do A, then C, then B, then D, and then E, right? There'll be a problem because instruction B need version from A, but you do it after instruction C. This is called write after read and write after write hazard. These are not true dependency. Right? If you look at the code in the program order, you don't have data dependency. It only happened because you start to issue things in a different order, right? In a different order. You need a different version of R3 for different line in your assembly, right? So we need to use register renaming to fix it. The solution we have already shown earlier. We rename the register ID with the ROB entry that hold the correct version, that hold the correct version. So we'll show an example here, right? This is my instruction window. Right? This is my register file. And this is my reorder buffer. All right, are we all with me so far? We are gonna go through this 4 line of code. We're gonna go through this 4 line of code. And then we'll do one step at a time. We do one step at a time. All right. So let's say register file initially has this value. R0 is 0, right? 2, 4, 6, 8, 10, 12, and 14. All right. Let's do it a little bit differently. Everything multiplied by 2. Why not? Right. And you need the valid bit for the register file, right? So here's the valid bit. I cannot. Points love to fight with me so much. Valid. Valid. And initially everything is valid. Right. Over here, this is the register file. All right, everything is valid in the beginning. Now, the first instruction is R1 plus R2. So you take R1, right? Source 1 from the reorder buffer is R1. What is the value of R1? Right now it's valid. You get it from the register file, right? 2, and then R2, the value is 4, right? The tag, let's just say is A, B, C, D, and E. Right? The tag is assigned when you allocate that row, right? Then it's not valid yet. You're computing right now is unknown. Not sure how do I do acronym for unknown, so I just do unknown. Right? You're adding right now. You fetch multiply, and also it wants to write into R3. Right? It wants to write into R3. So R3 is not valid. You replace R3 using register renaming. You replace R3 with A. Basically, this tells the CPU that if you want R3, you go look at entry A in the reorder buffer. That's the most updated version of my R3. Then you go to the multiply. Multiply takes what? You need what value? R3 and R5, right? What's R3? What's in R3? Don't know yet. Check entry A. So you can literally put in this source A, source 1, check entry A, right? Source 2 is R5, R5 is 10. Not valid, unknown. Right, so this is my add, this is my multiply, right? Now the third instruction, I want to add R4 and R7, right? R4 is valid, R7 is valid, so simple, right? I can do this. R4 is 8, R7 is 14, right? Not valid yet, unknown is still running, right? Oh, and I forgot earlier, when I need to update, I want to update R6, so R6 is gone. Not valid. You go check entry B, right? And then for the third instruction, you update R3 again. You add R4 and R7, you write the result over R3. So what do I do here? What do I change in the register file? What do I change in the register file? I change from here, right? To C. To C. You got the point. It's just the instruction that update R3 is the third instruction, so it should be C. Right, so this is my add, right? This is this instruction right here. The last instruction comes in. I allocate in the reorder buffer. The source is R3 plus R2. What is R3 right now? Is it A or is that C? Is it A or C? C, right? Because you basically go to the register file. Oh, not valid. What's the entry? C. So you put in source 1 as C. Source 2 is 4, 0, and unknown. And that's my add, right? And now let's finish this, right? Let's keep running and say, hey, reorder buffer is waiting for all this instruction to finish. Let's say this add finish first. The first add finish, I have what tag back, right? What tag is now back? Actually, before we go there, let me do one more thing. Hopefully, it doesn't confuse you that further. If I look at this for instruction right here, instruction A, B, C, and D, which one can I start running right now? Instruction A, B, C, and D. Which one can I start running? And which one do I have to hold and wait? A and C can run right now, right? Even though C comes after B, I can start right now. B and D have to wait for the earlier instruction A and C. All right, you got my point, right? Now you start to run things out of order. You actually start doing A, followed by C, followed by B, and followed by D. So that's now internally, right? Internally, you run out of order. All right, so internally we start to do things out of order. Now it looks like data flow, right? Let's say I finish A. Let's say A is done. Yay, right? Tag A is done. What I have to do is here, so to basically in the CPU, it would have a wire that connects to all the components that ask who needs tag A? Who needs tag A? Take the value here because it's now valid. Tag A is valid. And if you have a pending tag A, replace it with my result. What's 2 plus 4? That's 6. That's 6. The value of tag A is also now known, right? That's 6. Is that the oldest instruction? Is that the oldest instruction? Is A the oldest instruction? Can I retire? Can I kick this out of my reorder buffer? Yes, right. I can kick this out. And when I kick it out, what do I have? What do I do? I just need to update register file, right, with R3. Right? Or not? So let me ask you this. If I update register file that say, hey, R3 now has value 6, am I wrong or am I correct here? Anything weird with my register file? How about we come back to that later? But now we understand that A is the oldest instruction, right? Ideally, I can kick them out because I finished A already, right? There's no other instruction older than this, so I'm done. I'm done with A. And because I finished by this order A, C, B, D, right? Let's say the next thing that's done is, sorry. Let's say the next thing that's done is C, right? Which is this guy. What is 8 plus 14? That's 22, right? So I just go in and say, who needs C? Who needs C? If you need C, update yourself. Is now valid. The value is 22. What I have to do here is go here, and update here. Now C is 22, right? It's now valid. Over here, register is valid. The value is 22. Now let's say B is done. B is done. Basically, then ask like, who needs B? I mean, no one needs B except for R6. So you update this with the 6 multiplied by 10. So it has 60, right? And then you get rid of this because B is now valid. You update it with 60 and valid. Then you finish D, right? You finish D. It's 22 plus 4, right? So you erase this. This is now valid. And you update R3 over here, right? So that's 26, valid 26. My question that I'm gonna leave you right now with this question, right? Reorder buffer and register renaming seems to work perfectly, except this part become ambiguous. Because it has two things. It has the future version, but then it also have to maintain, right? Maintain the old version, right? It has a version that go ahead and update the entry with like a tag A, B, C, D. That's one version of my register file. Then you also need to maintain the version that the programmer see when you have exception. If you want to support precise exception, you want to make sure you maintain the version that finish in the same order. That's finished in the same order as the incoming assembly file, right? So that's what I want to leave with today, right? Now that we are about only like 14 minutes left until noon, So let's wrap up by ending this lecture right now. In the next lecture, next week, we'll come back and talk about more structure to make sure we have the correct pipeline here. So this is still not correct. It's getting there. It's getting there. But we still need to make sure for the register file, how do I maintain the version that support precise exception? And how do I maintain the version that aggressively put in the future tags into my register file, right? So I'll stop the recording right now, and we'll do the Q&A.